Okay.
Here we're going to see Andrea is doing about leveraging linked data fragments for enhanced data publication. Andrea is a software engineer with over 20 years of experience in various software engineering areas, from telecommuting to banking. He's an open source software passionate and Apache committer. His adventure with the search domain began in 2010 when he met Apache Solr and later Elasticsearch. Since then, he's been a search engineer in many projects in different fields: bibliographic, e-government, e-commerce, geospatial. In 2015, he wrote Apache Solr Essentials, published by Packet Publishing. In 2018, he founded his company, Spazio Codice. Since 2020, he is the tech lead of the Share VDE project, a library-driven initiative that brings together the bibliographic catalogs and authority files of a community of libraries in a shared discovery environment based on linked data. Andrea, please take it away.
Thank you very much. So, yeah, real-time RDFization. I don't know if the word is correct, but it gives you the idea. So we are going to see how in the ShareVD project we leveraged the linked data fragments approach for publishing RDF data. Sasha already gave a great introduction, so I'm going to skip this. So first of all, what is ShareVD? Is a library-driven initiative that brings together in a common environment, sharing the environment, the catalogs, bibliographic catalogs and authority files of a consistent number of leading academic and national libraries from North America and Europe. I would say that ShareVD is something like depicted in the image, something that sits in the middle between the different parties. Behind the scenes, we have a knowledge base, what we call a knowledge base, which is composed by a set of different storages where we store data. And let's see how it is creating during the ingestion process. We have different participants that contribute with their data. Data can be MARC or RDF data, and we have inbound API for providing streams of records or an integration based on file, on FTP or file exchange. So this data is pre-processed in order to enrich, duplicate, integrate the entities that are in the original data, and the result is what we call Sapientia, the ShareVD knowledge base. The domain model, the shape of the entities that are in the knowledge base is very similar, very close to the B-frame domain model. Here, the core hierarchy are depicted on the left. And you can see that it's very similar to the B-frame hierarchy. The main difference is that we split the responsibilities that are in the B-frame work across two different entities, work and opus. But I would say that apart this difference, the remaining part of the domain model is very, very close to the B-frame model. This is the graphical representation, the diagram that illustrates the contributions. So if you are, as I imagine, if you are familiar with the B-frame, you will see a lot of similarities. So the contribution, the role, the agent can be one of the four subclasses below. And we have other things, other entities like subjects, like concepts, like minor, entities that don't belong to the core hierarchy, like topic, date, place, event, and so on. And of course, they are connected with the entities belonging to the core hierarchies. Um, mm, what about the single entity? I mean, the agent, the opus, the work that we've seen in the previous slides. We call those entities prism. I mean, the fundamental entity of the Sapienza knowledge base is called prism. Why? Let's assume that a library uses Folio in this example to manage its data that is contributed to ShareVD. So in this case, a bibliographic record, let's suppose. That bibliographic record is pre-processed, and every entity that is within that record is detected and a bibliographic record is the instance, so the orange triangle with the corresponding attributes. But apart from the instance, maybe I have some connection issues. Let me know if apart from um, the main entity, the instance, the bibliographic record contains also other entities like agents, like publishers, like works, and so on, the small triangles. And we store the fact that those entities have been contributed by a given library. So in this example, I remember it was Stanford, maybe. Okay. Those triangles are contributed by Stanford. What happens if another library, another participant contributes with a bibliographic record that contains the same entities or the same bibliographic record, the same manifestation, I mean, uh, mm, it will happen the same process. And that library will create other triangles, but belonging to the same entities. The pre-processing phase is able to detect, to deduplicate those entities and to group the triangles that belong to the same entity. So, and that's why we call the grouped entity a prism. ShareVD, the system, gives a URI to each prism, and each prism always retain the different phases and the corresponding provenance of those phases. So here comes the linked data fragments approach. So this is the big picture of ShareVD, how it works. So on the left side, we have the participants, the libraries that contribute with their data and create the ShareVD knowledge base. Then the data is the ShareDB knowledge base behind the scenes is composed by different kind of storage, a relational database, an inverted index based search engine for providing search services, and an RDF store that contains RDF data. The first two are used in a GraphQL, are used, sorry, to provide a GraphQL and REST API layer for clients for the UI. And the third one provides the SparkQL interface over HTTP. The right part is out of scope for this presentation, but it is related to the Edit API. I mean, through a set of Edit API and an Edit UI called JCricket, we are able to edit what the ingestion process created in terms of entities within the the knowledge base. As you can see, there is a lot of redundancy because the same data is in different format for different purposes in three different places. Two of them are crucial. The RDBMS, because it's the primary storage, and the search engine, because we use a lot of search features that cannot be provided using another form of database, NoSQL, RDF store, or even RDBMS. We need a search engine. Think pasting, auto suggestion, aggregations, and things that you can see in any search engine. So our presentation is about the third part, which is related to the RDF store. We tried to avoid the RDF store at all because scalable solutions in terms of RDF store are very expensive. The open source scenario is not very good for these kind of products. And if you want to have something that scale, that with a high scalability, I mean, you have to use commercial products, which sometimes are very, very expensive because we are using a huge amount of data. So let's analyze a simple SparkQL query. So we have a first part which is used just to simplify the query below. So we have a selection where we define the variables that we want, that represents the data that we want to capture, and a set of query statements in terms of triples that represents the selection criteria. These parts can be theoretically executed in parallel and then intersected. So each of them can provide a partial view of the overall results before merging everything. That partial view is called a fragment, a linked data fragment. Or better in this case, when they are expressed in a SparkQL query, they are usually referred as triple patterns because the triple can be composed by three literals or one, two, or even three variables. So it more like a pattern. And so what are the participants of linked data fragments interaction? The clients, of course. Clients are those applications, UIs, and so on that are interested in request SparkQL data, better RDF data through SparkQL. And there is a SparkQL interface and a service that, of course, provides that interface. The difference between a traditional RDF store and the linked data fragment approach is here. The SparkQL HTTP interface and the storage is provided in the first block in case of the RDF store. It's more, how to say, monolithic from this perspective. In a linked data fragments architecture, the the role of this component is to provide the HTTP interface, the SparkQL over HTTP, destructure the several triple patterns in the selection criteria it finds in the query, and then delegate the each pattern to a simple service called Linked Data Fragment Resolver, which is in charge of exposing a REST endpoint, a simple and REST endpoint that is able to resolve a single triple pattern. I mean, a query composed by three variables, subject, predicate, and object, where one of them, two of them, or even three can be variables. And the linked data fragment resolver doesn't need to fetch the data from an RDF store. It can fetch the required data to resolve the triple pattern uh, using any storage. In this case, we are using a mix between the relational database and the search engine. But okay, it's up to the specific context of scenario and better architecture, because another architecture could have a NoSQL database behind. And the cool thing is that everything is executed in real time. So there's no need to store the RDF natively using an RDF store, but data is organized according to the project criteria in the relational database and in the inverted index. And it is transformed in it is translated in RDF according to a given ontology or set of ontologies on the fly. And that opens a lot of possibilities other than removing completely the RDF store from the architecture diagram. So yeah, this is a big picture saying that this is the same picture, but it focuses on the fact that the triple pattern server or the linked data fragment resolvers here are very, very simple servers that can be stateless servers, absolutely stateless, that can be scaled very easily. So you can have a huge number of instances of those servers that are playing behind the scenes. And this is specific to our case study. Everything was working, but with this high scalability, with the high scalability provided by those simple linked data fragment resolver, we met a bottleneck in the relational database. A relational database, in this case, Postgres, are not so good for horizontal scaling when you are talking about a huge amount of data. So we are moving, because the project is in progress, we are moving to a NoSQL storage that offers, unlimited scalability, horizontal scalability. Because otherwise, the architecture of the relational database became too huge and with a lot of problems in terms of maintainability, basically. So this is the same picture depicting the overall architecture, and using the linked data fragments, we just remove the third part. So what are the two examples of the benefits uh, of working in terms better translating and providing publishing RDF in real time? So one thing is the client using regular HTTP procedures like, I don't know, the header negotiation used for the content type negotiation, for example, can request a specific subset of data coming only from provenance A, B, and C. So I want, in this example, the client wants to get back the agent 201. The agent 201, as we know in the knowledge base, is a prism composed by the contribution of all libraries. The client here, through this custom header, but is just an example, wants to get back the agent 201, but it wants only the phases contributed by the University of Pennsylvania, Alberta, and Chicago. And this is very easy in this context because we know that we have a prism. Once detected the proper prism associated with that URI, we just need to select the phases we are interested in. And the RDF that is returned back would contain only those contributions. Using the same logic, sorry, this animation, yeah. Using the same approach, we could have the clients use another header for negotiating the shape, or better, the ontology set used for translating the data in RDF. So again, we do not store RDF using this approach. So that means that we don't have RDF in the system, in the storage, and we are able to create that on the fly. That means that on this request, we can answer for this agent using a mix of the Wikidata and yes, and BibFrame ontology, because the client requested that specific mapping. On another request for the same agent, we could use another kind of mix, schema.org and Dublin Core. This is possible because, again, we produce this RDF on the fly. And these are just two examples, and they are not alternative. So one client could request the same agent, the agent 201, using a given mapping code, which represents a set of ontologies that are used to produce the RDF. And using the header of the previous example, it can select only 4 provenances among the whole contribution set. Again, this is very, very interesting. This is very interesting, and we started thinking to this approach mainly for getting rid of the RDF store for, for cost reason, basically. But once we started using the linked data fragment, we found that very, very interesting in terms of potential things that we can introduce in real time, at query time. Okay. And I think that's all. Am I in time?
Yeah, that's wonderful. Thank you so much for sharing. That's incredible architecture. We have 5 minutes left in your session, and we did have one question in the chat if you have time.
Yeah.
We have one saying, are you saying individual components of the triple can be more complicated than a single element? There was a conversation yesterday about including quads or quints instead of triples. Is this related?
Uh, Individual components, you mean just the component, the API component on the right, because these individual components are not more complicated. I would say that are simpler than a monolithic server that must satisfy the whole execution path of a SparkQL query. In our example, here we um, we would have, let's assume, 1, 2, 3, 4, 5 linked data resolver that are in charge of resolving only one triple pattern instead of like what happened in a monolithic RDF store, where the server needs to execute the whole query. There is a price to pay for it's not everything free, let's say, because in a monolithic storage, the server is in charge to execute the whole SparkQL query, which is more expensive, but it gives space to a huge number of optimizations because the server controls everything in the same place. Here, every triple pattern is delegated to a remote server. So the role of the SparkQL server here, sorry, the role of the SparkQL server here is just to deconstruct the different, separate the different triple patterns, delegate their execution to a simple component, get back the result from all the resolvers, and merge the final result before returning everything to the client. There is a bit of space for optimizations, but of course, as you can imagine, the latency and the space for optimization is the latency could be a problem, and the space for the optimizations is smaller than a traditional monolithic RDF store. I'm not sure if I.
I think that was helpful. And I know Jim was also helping to kind of resolve that
Okay.
question in the chat. But Amanda said this, it was beautiful explanation. So we appreciate this is such a creative solution. We're at time now. If you still have a chance, I didn't see any additional questions in the chat, though some may come through. But we appreciate it so much. Thank you for sharing your work with us.
You're welcome.